dynamical sampling and frame. So I'll explain what dynamical sampling is, and then the way it relates to frame, and and at the end I will give you a general view of some of these problems in dynamical sampling. So what is dynamical sampling? So it's just sampling functions that are evolving in time, and there's some operators. And well, frame, for many of you, not all of you already know, it's a system that behaves kind of like an orthonormal basis or Riesz basis, and I will define that, and I'll show some connection between the two, and so this is how the talk will be. So this work was motivated by some paper of Yu Lu and Martin Vetterli. Martin Vetterli now is the president of École Polytechnique Fédérale de Lausanne. I don't know how, maybe his work have something to do with that. And Yu Lu is his grandson. He is a student of Minh Do, and they had a very nice paper in a conference paper that I was reading one day, and I could not understand, and I thought, but it's interesting that I don't understand it. So what do when you are in this situation? You ask a student to look for, to understand it, what I did. So with a student, Jacqueline Davis and Ilya Krishtal, who was visiting me, we started looking at this area. And so I will describe a little bit what, at least one of the problems that I'll be talking about. So here's the problem. So you have a function f, which is unknown. In this case, for this particular example, I'm going to take it to be L2 of z. And you want to know this function, so you sample it. So this z here is depicted at these black dots and red, and as well as the red dots. So this is z here. And this function f is sampled as at time t equal to 0 at these red dots, and obviously that is not enough to recover f. So by here sampling is, I put g1, it's a function also, f inner product g1. This is what so you measure f by hitting it with a functional, with a vector. So you have this information on the red dots, but behind all of this you have an operator a, which is an evolution operator, and af is your new state, and you sample this function again at these red dots, and you keep sampling. Maybe you stop at some point here, and you ask yourself, under what condition on the operator A on the sampling set I, and the number of time sample that you take at each I, under what condition can we recover the function f in a stable way? So this is the problem, and one of that I will be talking about. And so mathematically, you just have a bounded operator in some Hilbert space H, a countable subset of the Hilbert space H. Those are the functionals that you're going to apply to a to the power tf, and those are your measurements. So those are the samples. T vary in some set, could be from 0 to L, or discrete, could be discrete, like the example I showed you is a discrete set. So you have this function which is evolving in time, and there's this operator. You hit it with vectors, g, and from these measurements, you want to recover f.
Is A linear or not necessarily?
A here is a linear.
Linear.
Yeah. Okay, so can we recover f from measurement? We want to recover f in a stable way, and so before I go on, let me just give some definition, just to set things, the notation, etc. So we have a countable subset of H. We have some subset of R, which can be discrete or not. And we have a set now, a to the power tj, where j runs through this set and t round the time run through this set. And we will say that this is Bessel, this E is Bessel if we satisfy this inequality. Now if mu is discrete, this is just the usual Bessel inequalities. We're going to say that this set is a frame if you can find two positive constants such that this pair of inequality hold. And again, this maybe sometimes I'll refer to as semi-continuous frame. And if mu is discrete, you get the typical definition of frame, the Duffin-Schaeffer original definition. Okay? So this is just some definitions.
Okay, well, is A positive operator?
No, okay, so that's a very good question. A cannot be completely arbitrary if I want T to vary to be anything. So A can be anything if if I'm, for example, taking integer powers. If I'm taking, so let's say T vary between 0 and L, then A cannot be obviously any operator. It will be hard to make definition, but a normal operator then would work. You can use the spectral theorem, and then essentially you can define that. So that's right. So this definition of A cannot be totally arbitrary. It can if this is an integer. It will not be easy to define, but unless A is normal, for example, then this is okay. You can define it via the spectral theory, and positive would work, of course. Any other question? Okay, so the question again is, can we recover F from these measurements right here? And the answer to that is, well, we can recover it. We want to recover in some stable way. Stable way means I want to be able to take this set of measurement, which is say in L2 of J cos tau, and recover F by the inverse operator, but we want this inverse operator to be bounded. That's just by picking this, putting on this side, we get A star TG, and basically this is equivalent to saying that we want this system right here, A star to the power TG, where G runs through here, T runs through here. We want this system to be a frame. So the problem of recovering the function, the initial function F, from data which are samples, when the function F is evolving in time, and an operator A is equivalent now to simply looking at a system of this form and asking whether the system is a frame. Okay, so now we can completely forget about where this problem came from. And this is a purely mathematical problem. We are given a set, subset, a countable set of a Hilbert space H, some subset of the time tau, some operator A. We take this to the power T, apply it to G, we let these things run here, and we want to ask ourselves, what are the conditions for which on A, this set J tau, for this to be a frame of H? So this is the problem. In fact, here is stated. No. So G could.
Because you say you want the AT of F at I in the EL+.
That's right. That's just one of the possible functionals. Okay. But you can make it. That's right. So sampling would be essentially the functional be like the original problem would be just the delta being Dirac. But you don't have to have that, right? It can be anything. So G could be, for example, some sort of, if we're in a reproducing kernel Hilbert space, then yeah, exactly like you say. So let me talk a little bit about this problem, and so I will take. This is a problem on sampling, so I'll sample a few results, and I will give you some idea about various things we have done. And just to give you a flavor of the type of problems and their connection to other areas. And then at the end, I'll just simply give you an idea of various other problems, and different from the one that I'm giving, which many of them are open, including there are many problems here that are open. I'll talk a little bit about that. And some of these problems that we have been working on for the last about 6 years or so. Okay, so I'm going to take the special case right now where the time here is just integers, 0, 1, 2, etc. And I'm going to go to infinity, so this is a special case. And this kind of sets a little bit the thing. So here A can be any operator, bounded operator. And so the first thing that we realize that if this set, which is given here, a to the power n, g and j, n is positive and goes to infinity, is a frame for h, then it must be true that the orbits of f must go to 0 as n go to infinity, of a star f must go to 0. Is that okay? So this is it is necessary condition, and let me just give you an example and show you how, on an example, what this looks like on a very specific. So suppose we have h is that's L2 of n, and suppose a is just the right shift operator.
What's L here?
I'm sorry?
What's L here? What is L here?
This?
The number is the number.
Yeah, sorry. So this is just, I'm just saying, so n go from 0 to capital L, and I think this is just n go to infinity. So forget about L. It's irrelevant for this, sorry. I had it slightly differently at some point, yeah. So I had it n go from 0 to L and let L be infinity. So, yeah. So you let A be the right shift operator, and suppose the set consists of a single vector, which is 1, 0, 0, 0. And if I apply the right shift to the 1, 0, 0, 0, what I do is I shift the 1, 0 to the right. So I get essentially the Dirac at n, if you like. And so an E1 is En. And as n goes from 0 to infinity, well, this is just, in fact, an orthonormal basis. And so that's just a very easy example. But you can see that also how this A star n is simply the shift this way. And if we take n to be large, then xn, we have this sequence that starts from xn to, that goes this way. And x is in L2, so we can see that A star and f go to 0 as n goes to infinity. Sorry. Okay, so this is just an illustration. So, but what this tells you also immediately, that if A is a unitary operator, then obviously this cannot happen. A star n, f cannot go to 0. And therefore, this set a vector is not a frame if A is unitary. So that's a direct consequence. So of this, so let's see. Let's try to understand what this example and kind of see what's going on here. So I'm going to take the exact same example, except that I'm going to replace n by z. So A is a right shift operator. The set is just the single vector E1, and I apply A to the power n to this vector, and what happened is that this is not complete in L2 of z. So almost the same system up to just this variation. So what's happening here is simply A is, in this case, is unitary. And you simply cannot get neither a frame nor a basis or anything. So you get an orthogonal set of vectors in L2 of z, but it is not complete, and therefore it is not a frame. Is that okay?
I understand your A. Now the vector is on all of z.
That's right.
And what happens to the left half?
No, that's right. So I'm doing just positive. I'm doing only positive.
No, but it's the way you wrote it, because it should be by infinite. The way
Vector x should go from minus infinity.
the way you wrote
Yeah,
it is a little ambiguous, because but we know what it means. It means you take x minus 1, x minus x 0, this, and
You just shift it.
and you just
There's no
shift.
zero.
No, there is no zero. It's okay.
Okay, well, okay. So
The sequence should be in Z, not in
You said that x was a sequence indexed on z, not on n.
yeah. Oh, what this means, right? Oh, sorry. Yeah, that's right. So this it's a bi-infinite. It doesn't start at 0. Sorry. So this is not a finite.
All right.
This way. Okay. That's a problem with copy paste nowadays.
Blame somebody else.
Yeah. Okay. So here is another thing that happened. So if you take A, which is normal, then I mean, we have seen that for this previous example right here, you can get on this example simply an orthonormal basis. But if A is normal, then you can also show that in fact, no matter what your set G in H, then this guy right here is never a basis for H. So you cannot get basis of H for normal operator if you take positive power. And essentially, you always get some sort of dependence, linear dependence, and if you are a normal operator. The other thing that must happen for you to get a frame, at least in the case where the set G is finite and the dimension of H is infinite, is that this set here, if this is a frame at all, then the norm of A has to be larger or equal to 1. So together, if you look at for infinite dimensional Hilbert space and for finite set G, if you look at this result tells you essentially that the spectral radius of A is less than or equal to 1. So you know that for normal operators, that this A have to essentially have norm 1 for you to obtain frames. And so the first frame that we were able to obtain by iteration using a single vector this is the result for it. So suppose you have a bounded normal operator and you have a single vector G, and here we are in dimension infinity, and we ask yourself, under what condition on A and G do we have this iterate a frame for H? And it turns out that this is an if and only if statement. You can only do that if A is essentially a diagonal. If you look at this, this tells you essentially you can represent A as a diagonal matrix with all the lambda J different. That in that case the eigenvalues lambda K must be in the unit disk. They must go to 1, and they must satisfy this constant condition, which is a condition that is Carson used for the interpolation on the H2 of the disk, and you have to have this condition on the eigenvalues for some delta bigger than 0. This is the condition that must happen on the operator A, and the vector that you apply A to must also be special. It's not any vector, or there's a bunch of vectors, but they have to be special. They relate to these eigenvalues as follow. This essentially, you can look, this is the component of this vector J at J, and this component is essentially this value up to some constant. So this is an if and only if conditions. So basically what this theorem says, that if A is normal, well, we know we cannot get basis, but we can get frames by iteration over a single vector. But operator have to be very special, the vector G have to be very special, and this is what you get. So is there any question about this? So there is a generalization of this theorem, a very non-trivial generalization, in fact, and for the case where this is not a single vector, but in fact it's finitely many vectors. And there is an extra condition which I think, well, it's complicated to understand, but I just want to say that this result have been generalized recently. Okay, so now I talked a little bit about frames that are obtained by iteration with integers. So a to the power n, where n is integer, and we're taking n to be all the integers. I'm going to switch now to another example where a is actually a normal operator. This set G is a Bessel system by itself. And so a to the power tg, and t now runs through an interval 0L. And the question is, under what condition is this a frame? So what I want to say here is this is the case, for example, where you have measuring device that are constantly taking measurement, and they are setting in space at different locations, and these measurements are just continuously obtained from, say, 0 to L, and you ask yourself, okay, when can I recover a well, when is that actually a frame, or the same equivalently, given a set F, can I recover F from the measurement I showed you before? And it turns out that, in fact, there is a relation between the semi-continuous frame and this discretized version of them. And this is often something that have been done in wavelets, and it is often something that we like to do. What if happens if we discretize a frame? So if this is a semi-continuous frame for H, then we know that there are finitely many discrete times, 0 to L. As long as these times are sufficiently close to each other, then the discrete system is also a frame for H. So if you have a semi-continuous frame, you can always discretize it and get a discrete frame. And the converse is also true. If you have a frame which is a discrete frame, a to the power TIG, and TI is set of finite set of times, and if this is a frame, then you can also say that this one is a frame, but with some extra condition. This is A here have to be invertible. If A is not invertible, you can show that, in fact, you have counterexamples. So A here really, you need to be invertible in order to be able to go from this to this. Okay? So what this says also, if the dimension of H is infinity, then obviously this result tells you that the set, the spatial sampling set, if you like, has to be infinite if we are infinite dimension. Okay, so let me say that there is a very general result about discretizing frames, so if you have a continuous or semi-continuous frame, you want to discretize it, and to get a frame, when does that happen? There is a relatively recent result by Freeman and Spiegel who tells you how and when, but it's very general, and this result is a little bit finer because we have more specific situation. So this is what I want to say about this. The other thing that is interesting is the following result, which is my student Long Shou and my other student Armenak Petrosian, that so suppose A is invertible, self-adjoint, and the set J is countable, and I take A to the power Tj, and we know that this is a frame for 0, 1, then it turns out that this guy is a frame for 0L for any L. So in fact, basically, if you get this system to be a frame for any interval at all, then it is true for all intervals. And what this is not surprising if you take, for example, suppose this is a frame for 0, 1, and you take L bigger than 1, then that the fact that the new system is a frame, that's kind of obvious. The less obvious is that you can take actually L be less than 1, and that's and this result is actually at least is interesting because it used a lot of complex theory and some interesting mathematics. Anyway, so we were able to do this to prove this result for the case of self-adjoint operator. We believe the same is true for normal operators. We don't know for sure. We have no proof. So here is one thing if you want to help us. Now let me tell you a little bit more about see how much time I have. Oh, I didn't push start, so how much time do I have?
We have 20 more minutes.
I have a lot of time. Okay. So I show you one problem in dynamical sampling and a few results. Again, it was some sort of to give you a taste of the kind of things. So the result that I show you rely on, the proof rely on complex analysis, rely on certain, on the, often we use spectral theory when we have normal operators. There is a lot of function analysis techniques that we use. But there are many other problems that in dynamical sampling that you can look at. And I'll talk a little bit about a few that we have worked out and a lot of others that we didn't. Some of my collaborators here that have worked on these problems, some of them are my students. For example, Jacqueline Davis, Armenak Petrosian, Sui Tang, and some others are postdoc like Rosa Seska, which and a lot of my collaborators, and some of them are here, Ilya Krishtal, and some engineers, and I'll tell you a little bit more about what we have done with them. So there is a lot more problems that are can one look at, and the first problem would be, so A was, so in general, most of the time that I, on these problems actually was a general operator, well, or normal operator, but what happened if A is actually convolution operator? And so that's, you can sometimes get more, and also this is maybe more what happened for a physics problem in which you have a PDE or behind, and A is essentially A is a semigroup, or A to the power T is a semigroup, and I showed you here the G that I talked about, that I showed in most of the theorem, was mostly general except for the first picture. Well, no, not even the first picture. So it was just a general. But you can take this set G, which represent sampling in space, if you like, to have some structure. So a lot of the problem that I show you, G does not have structure, but you can put some structure on G, so some group structure or some other structure, and you can combine that with A being convolution or A being just general operator, etc. And that give you some other interesting things, and also has some applications, because often in application you also sample in uniformly if you can. Here in everything I showed you, it was a known operator. Sorry. It was a known operator, so a bounded linear operator. But what if A is a known operator? Well, so you don't know A, you don't know your initial function f. You sample both in space, that's correspond to the set J, and in time, and you ask yourself, can I get both f and A? And that's actually a problem which seems to be, so it's nonlinear. It also seems to be, is it feasible? And in some cases, actually, you can find both A and F. What you can find is you can get a lot of information about the spectrum of A, even though A is unknown. And if you know a little bit more about A, then you can find A and then also F, the function, then known function F. So this is some problems. We have tackled some of these problems. There's another interesting problem that we have tackled a little bit, and which is your measurement are phaseless. What I mean by phaseless is that you don't know F inner product G, or the sampling of F, if you like, or AF, etc. You don't know, but you know their modulus, and in this case, the problem we looked at, Hilbert space was real Hilbert space, and so those are absolute value. So you know the absolute value of the samples, but you don't know, and you know the operator A, and you want to be able to recover F from these absolute value. Of course, you can recover F, if at all, up to a sign. So you can recover F or minus F, but you can't expect more. So this is some problem also that is interesting. We have looked at the real Hilbert space, the complex Hilbert space. We don't know how to do that. So this is another problems that we found interesting. Now the general operators that are not necessarily normals, of course, you have to restrict things like T cannot necessarily be an arbitrary number, but there is a lot of things that can be done there. We have done a little bit. I've shown you a few things, and but I think this area is also totally open, and what can be done is up to you. So something else that I want to talk about is numerical algorithm. So when I say we can recover something in a stable way in that problem that I just showed you, this specific problem where A is known, I sample both in time and space, and I say, can we recover F in a stable way? So that is kind of related to this frame theory or frame system. But one of the issues is that these frames, they have constants A and B, and these constants can be very far apart. And if, depending on the sets that we have, the ratio B over A can be very large, and that means that we have certain instabilities. Or, I mean, stability, but it's kind of the condition number is small, which means one has to do also something else to try to kind of make things better or recover things in a certain way. And so there are a lot of things that need to be done there that will, in case where the condition number are bad, what do we do? Finally, we actually had fun a little bit. We have a couple people at Vanderbilt who is in, I used to say ISIS because that's the way they, but now I can't say that because I'm afraid but it's the Institute of Software Integrated System. And so they actually, we decided to see, you know, okay, we have this theory where A is unknown, where the function f is unknown, and where we want to recover f and a in some way here. So can we do that? So we have the theory, but we want to test it a little bit in real applications. So we got with them, and they actually went and bought a bicycle wheel, and they plugged a few electronic thermometers, and they heated up this wheel in several ways, and they let the the temperature kind of stabilize and just measure the temperature all around the wheel. And they just gave us temperature data. We know nothing. Of course, they don't know much about the wheel either, because it's just a bicycle wheel. And so for us, the problem was, we have let's test if our algorithm even have a chance of working. So what we did here was, I think we had about 15 or 45, I think 45, at least one of the experiments we had 45 thermometers. And so that means we have measurement in 45 points, and the measurements are in time. So what we did was we subsampled. So we took, instead of all of 45, we took 15 of them, 15 of these sampling, in spatial sampling. We looked at that. We recovered our, what we expect is both the operator A, which basically that has something to do with how things propagate here, the operator that make things evolve, and also the original function. So, and after we did that, we compared to the other, so we took only 15 out of the 45 measurements, we reconstructed, and then we compared what's left. And it's okay. Of course, we also, we get sometimes 10, 15, up to 30% error, but still for us that we were pretty happy with the experiment. Let me tell you a little bit. So this is just some short list of some things if you're curious and want to see what kind of things have been done, and there are some other citation there you can look to. But so Ole Christensen and Marzieh Hassananab decided to look at this problem in a different way. So they asked the following question. They say, suppose you are given a frame, so you know a frame, and they ask the question, under when can you say that this frame is a frame that comes from the iteration of a to the power n j for some j and for some n? So that's the question they looked at, and they have a couple papers, actually several papers, but there's only a few of them here. And this is an old, I guess, archive where they have various problems that are also open that talk about this kind of different problem, kind of almost the opposite. There are others like this is actually I think this may have been now published. This is the paper where I told you this first theorem that had been generalized by this group, where you take an operator A to the power n and go from 0 to infinity, and you ask yourself, and there's a single vector, and you ask yourself, when is this a frame? So there's sufficient conditions there, and you can actually do this for finite set of vectors, and this is what's done here. And here's some couple papers, 2 or 3 papers that we have done that are about some of them in which the operator here is I think this was the first paper with my student Jacqueline Davis and Ilya Kristol. And this was really for us to understand. It's a very simple paper. It's finite dimensional. And in fact, in that first paper, we say, it's funny, you say, we think that the general problem is too difficult to do. And of course, that was then. And the thing that we thought was too difficult to do, in fact, we know how to do, and we have done a couple of years later. So this is another paper with my student Soy Tang and my collaborator Carlos Cabrelli and Ursula Molter, and this other one with my student Armenak Petrosyan and a postdoc Sakmak, Ahmed Sakmak. And so anyway, there are more, and I just wanted to give you an idea. So I think I want to stop here, and okay, thank you.
Are there any questions for the speaker? Yes, please, Boris.
You said G is the same for all T. Did you consider the case when this set G is different from?
Yes. So, of course, this is you can, and it becomes also more complicated if you just consider that. In fact, I would say that the ultimate goal, the best problem that one can do, would be that you have the G cross T, and you kind of take some random sample. That would be the ultimate, and that's difficult. We don't know how to tackle it yet. So there are some. One of my students did some problem in which they changed G. Here, G, by the way, is changed in this following way. It's a nested sequence, so we can stop like the wavelet. So the first one is a bunch of samplers, but the next one could be less, but a subset of that. So in some sense, it's changing, but not changing in the general way you think. So there is a way of course, there is another problem that my student Jacqueline Davis did, where you actually kind of shift the same G, but shift it in time. And those are the only two situations that I know where, well, this is the one situation I know have been done. But the general problem, which I would love to know how to do, is I think very difficult. But yeah, there is nothing there yet.
Another question?
I once heard a talk about a similar topic where they were saying we would like to observe pollution, and therefore we mount sampling on buses which are running through town. So that would be different sampling at different times, but with a certain natural structure. So do you know anything in that, whether anything has been done in that direction recently?
Right. So there is a paper. In fact, I believe that paper was Martin Vetterli, maybe the one you heard, with Jose Luis Romero, and one of Martin Vetterli's student, in which that's right. So they actually have a bus, a real bus, with some sniffer, and they go drive around, and they actually measure the pollution data by measuring using this bus. And I think maybe Charlie here probably knows more even about this. And that's right. So they have some results there about that. They make assumptions, of course, on several things. So it's the restrictions is that the I think the function are band limited. Is that correct, Charlie? And then there is some other assumption that I'm not sure what it is. And there they have some interesting results. That's right. So they do have that. And with Charlie, actually, and Jose Luis Romero and Ilya Kristol and Philip Jamming, and we are trying to do something in which kind of similar but much simpler, in which we kind of yeah. So anyway, yeah.
Other questions?
Have you compared or discussed your results with people in control theory? Because I think,
Yes.
okay, in identifiability they formulate a lot of questions in terms of proving that something is a
This is
prime.
This is true. You're absolutely right.
But
And
they
the,
have special PDs, I mean, they have very specific model in mind. Do they fall in this category? And maybe
Right, so you have something very pointed here, because this is right. So this one can look and say, well, this is really in some sense a problem of observability, right? So we know that there is some connection. In fact, we haven't pursued it too far yet, but there are some connection, obviously. This is, and I want to say that the closest thing that is related to some of these things is by a Russian mathematician who's now in France. But the name is not coming to me right now, who've done exactly this kind of, long time ago actually, this kind of abstract theory that relates to, No, it will come to me, I'll tell you. Sorry. Okay, come to me.
Okay, Ron has a question.
Ron.
So I have this operator A in your set G. Why don't you have a theorem that tells you when the null space is trivial? I mean, first theorem I would try to prove is when you have enough sampling information.
Well, we have these results, of course. The fact,
So does it have to be a frame in order?
no. So I didn't present,
So the frame is for stable.
so the same for stable, that's right. So the question that you're saying, well, I mean, there are a lot of problems that we could ask. For example, when is the system complete? When is the system a respaces? When is the system a basis? When is the system, so there are a lot of questions that we did ask.
The characterization when null space.
Actually, this has to do with, so for normal operators that we know, and for normal operator you have to look at the, essentially the spectrum, and the spectrum cannot separate the complex plane into two different sets. So for example, if the spectrum is a circle, you're into problems, and it has to be also somewhat nice. So we do have these results that tells you exactly when things are good for completeness. But that's a much different problem, and it's easier in a way. It's much more difficult.
I think it would be an elegant description of exactly when you have completeness.
Yeah, no, completeness is a lot easier. Well, you know. So.
Okay, well, let us thank the speaker again.